Hello everyone, welcome to my presentation. My name is Ziying Liao. I am currently a master at National Taipei University of Technology in Taiwan. I'm very happy to have this chance to give this presentation. The name of our thesis is Unidentified PII Detection with a K-nearest neighbors approach. First, let's introduce what PII is. PII is abbreviation of Personally Identifiable Information. Personally identifiable information includes any information that can be used to distinguish or trace an individual's identity, such as name, social security number, date and place of birth, mother's name, or biometric records, and any other information that is linked or linkable to an individual, such as medical, educational, financial, and employment information. Examples of PII include that are not limited to date of birth, place of birth, business telephone number, business mailing or email address, race, religion, geographical indicators, employment information, financial information, such as this. After introducing PII, let's talk about the background of the thesis. In order for an enterprise to meet its customer expectations of service, its customers are often required to provide certain information for or feedback on the service provided. The information provided by the customers may include their personal and confidential information. In light of the EU GDPR and the legislation on personal data protection in Taiwan, enterprises will be at risk of low valuation if they do not have adequate information management infrastructure in place. The standard of ISO 29134 mentions that the process begins with an asset inventory, and this step will find out PII. The next steps are risk assessment and risk treatment. Finally, complete the assessment cycle. In the past, each stage was mainly carried out through manual sampling, and there were often omissions. Our paper is to solve this problem, so we have the thesis. So we propose this approach. We use machine learning to detect the identified data in order to find out identified data. The data should be recognized as an PII, but not. Before introducing our method, we first discuss related works. Very few academic works have been carried out on this topic. Some study on risk assessments, risk predictions, and anomaly detection by machine learning are mentioned here for informational purpose. We list three related works for discussion. The first one is Eminagaoglu et al. Studied of information security risks of a human resource department of logistics company. 11 machine learning classifiers were used, and 342 samples of HR data were collected for their study. However, the number of samples used in their study was too low to be sufficient for effective training and testing for machine learning. The second one is that Zhao et al. Used web-developed neural networks for information risk assessments. Web-developed proposed the WNs to avoid shortcomings of BPMN. The WNs were known for their strong learnability and high accuracy. The WN's neural network architecture was also relatively simple, and they can achieve convergence of speed more quickly. The WN models are more suitable for quantitative than qualitative analysis. The final one is Paltrinieri et al. Research. They use deep neural networks to predict risk associated with oil wars. Kaplan et al. Defined risk as a combination of answers to these three questions. One is, what could go wrong? Scenario S. Two is the likelihood of that happening, probability P. The final one is the severity of the consequences C. And the function is R equal F SPC. In Paltrinieri studied the exam each layer of the risk factors. For example, how equipment at the oil wells was operated, what accidents had occurred, and how experts could have prevented the accidents. These factors were then used as indicators for their risk assessment models. The output of their models represent the probability of accidents occurring. After introducing the related research, first introduce the data set we use. Our study data was collected from a list company in Taiwan. The dataset contained 4,096 information assets, each of which has three variables, including asset names, asset attributes, and PII. And this is our implementation process. There were 4,096 raw information assets in total, all of which were pre-processed. Asset names of the raw information assets were segmented into words or phases. As our main task was to identify PII of the company's customers, uncertain data or data with missing values were removed from our study data. Data relating to employees of company or internal correspondence was also removed, as it had negative impact on our machine learning training and was not considered PII for the purpose of this study. Duplicate words, punctuation marks, stop words, building for numbers, and words with only one Chinese character were also removed. There were 1,104 words or facets segmented from the asset names remaining, each of which was then treated as a feature of the current inventory, totaling 1,104 features. There were 47 categories of asset attributes in the raw information data. All of the 47 categories of the assets attribute were treated as one feature. Each category was given a categorical number, representing the numerical value of the entry in the dataset. After word segmentation and classification of the asset name, and the asset attributes of the raw information data, there were a total of 1,105 features for our model, containing both PII and non-PII information assets. Our model was then used to process the features for PII detection. After the data was pre-processed, it was arranged into 1,225 rows of information assets in our inventory. 80% is trained data, and 20% is test data. And we find basket through grid search, and we used KNN as our classifier. And this is our result. We have test data, 245 rows data, in variation 22 rows data, and the 22 rows data is asked for to mark the data for PII. 245 rows of data in the inventory were tested with TF-IDF and 100 encoding in our model. The F1 measure of test data was 82.93% and 83.42% with 100 encoding and TF-IDF respectively. 22 rows of data in the inventory were tested with TF-IDF and 100 encoding in our model. The F1 measure of invariation was 81.82% and 63.33% with 100 encoding and TF-IDF respectively. TF-IDF scored higher than 100 encoding in test data, but there was not much difference between TF-IDF and 100 encoding. However, in terms of the overall result of the model, 100 encoding scored higher than TF-IDF. 100 encoding was therefore chosen for our study due to its stability. And we also did another experiment, a hierarchical KNN model. It, like the single KNN model, processed data through word segmentation and assigning categorical values to asset attributes. However, a hierarchical KNN model consists of 3 KNN models. Our results showed that the 100 encoding KNN model was better than the hierarchical KNN model, as the F1 measures of the single KNN for both the cost validation and evaluation were higher. In our study, we used KNN models to detect unidentified PII. 3 models, namely the TF-IDF with single KNN, 100 encoding with single KNN, and the hierarchical KNN models, were tested in our study. Our test results that showed that the F1 measure of the TF-IDF single KNN model was lower than the 100 encoding single KNN model, possibly due to the fact that the data used for our study was not populations, that the frequency of the word appearing in different samples was different, and that it had no positive impact on our target variables. The reason why the F1 measure of the hierarchical KNN model was lower than the 100 encoding KNN model was that the number of asset attribute features used for training were insufficient and that assets shared the same asset attribute might include both PII and non-PII assets. The use of asset names for training, however, resulted in better detection of PII, as both asset name and asset attribute were used in the combined KNN model of the hierarchical KNN model for training. The F1 measure of hierarchical KNN model were lower than 100 encoding single KNN model. The KNN model proposed in our study utilized simple machine learning to explicitly determine whether any row of data might contain PII, and it could help reduce the time required for audit and professional cost. And in the future, our KNN model will be offered to auditors to be used in their auditing for feedback on the predictions given by our model. A second one, we want to add the column. The column is business process of an enterprise, and it represents the relationship between the use of an asset named in the business process of an enterprise. The final one is to do the time evaluation for our model. Thank you, everyone.